Hello IB Psychology students. Here is a PowerPoint to help you carry out the Inferential Statistics tests, either the Mann Whitney U Test for independent measures or the Wilcoxon T Test if you have used repeated measures. If you follow the instructions step by step, then you'll find that these are very straightforward tests to carry out. But I must stress that you don't think, oh, this bit's easy, I'll just rush ahead here, because you may find that you've missed out a very important step and then your stats will all be incorrect. So do follow it step by step. Okay, oops, what's happened? My PowerPoint's always doing this. Right, okay, so we're starting with the Mann Whitney U Test. So what you need to write in the analysis section of your IA is you simply state why you are using the Mann Whitney U Test. So follow this part of the video if you used independent measures. If you didn't use independent measures, if you used repeated measures, skip ahead in this presentation to the Wilcoxon test. You don't need to follow these instructions if you used repeated measures. So you should be with me for the next part of this presentation for quite a while until we finish the Mann Whitney U test. And that is if you have used independent measures. So really you start your inferential stats section of your analysis just stating this is what you're using. You're using this test because you've collected ordinal level data. That's just simply data that can be ranked, because you're going to be looking at, you know, who got the highest score, who got in the middle, who got the lowest score. It's not data that exists kind of independently like interval level data does on say a temperature scale or a ruler. It's data that you have kind of created from the measurement that you've set up. Okay, so next thing, what you're looking for is something called the U value. Now, to determine your U value, you have to be clear about how many participants you used per condition. So this is important to know, you know, did you have 9 participants in one condition and 8 participants in the other condition or whatever? You look at your data, you will have that information. You're working at a probability level of 5%, that's 0.05. You don't need to worry too much about this. It simply means that you are testing whether the results you had were the result of the IV's effect on the DV or other factors. So the 5% probability level is whether you have equal or less than 5% probability that your results were due to chance, or to, you know, whether they were actually due to, less than a 5% probability that they were due to chance. That gives you a good margin to claim significance. You don't really need to know very much more than that, unless you want to expand on that a little bit in the analysis section or maybe in the evaluation section. All you need to know that if you find significance at this 5% cutoff level, then you can say that your independent variable has affected your dependent variable. You have a significant result. If you don't find this, if your stats tell you it's not significant, then what you do is you have to accept your null hypothesis. But that's fine, because you can just pick that up in the evaluation and talk about why you think that happened. Okay, so what you do first of all is just list your scores per condition. So we have scores for condition A and scores for condition B, and make sure that you leave some space between each list. This is what your scores should look like. This is an imaginary data set. I just threw these numbers down just because, you know, we want to have something to work with. I didn't go out and run an experiment and collect this data. So you have got condition A. Let's say you've got your scores for condition A here. Leave a space. Make sure that you've got this word here, rank, above here, because you're going to be ranking your scores. Then you've got condition B here, and the same thing, you have rank. And we'll look at why you need that rank right now. What you need to do is rank the scores. So you start with 1 as your lowest rank. You find your lowest score. You give that score the rank of 1. And you just keep ranking across the conditions. You don't rank condition A and then rank condition B. You rank the whole data set. And what I'm going to explain in a minute is how tied scores are ranked. So let's have a look at how this works. So the scores that we're ranking we've just seen on the previous slide. Now before we look at how to rank these scores, I just want to tell you something about tied scores or repeated scores. It is more than possible, it's more than likely really, that you will have participants, more than one participant who scores the same, the same number of points. Let's say you have, 3 participants who all get 8 items out of 10. That's perfectly possible. Now what you're doing though is that you have to rank your scores, and scores can't all be given the same rank. They can be given the same rank, but what I mean is that rank has to represent where they sit in terms of the whole data set. Now, if you're now thinking, what on earth is she talking about? Don't worry, I will explain it. Now, what you do is use the median of the ranks to decide the rank. Now, in this data set, as you will see in a minute, there are 2 scores of 11. Now, 11 is the second lowest score from this data set because 10 is the lowest score. So we give 10 the rank of 1. Don't worry, I'll show you all this in a minute. As there are 2 scores of 11, they both can't be given the rank of 2 because there are 2 scores. So they don't actually rank second because they're taking up 2 places on your ranking scale. But you can't give one a rank of 2 and one a rank of 3 because they're the same score. So you divide the ranks between them to account for the value of all the ranks. Now, at this point, you might have thrown your laptop out of the window and said, Miss, what are you talking about? Bear with it, go with it. So, for example, score of 11, 11 is our lowest score. We can't give the 2 11s both the rank of 2, so we give them the median. So our first rank was 1, which score number 10 was. So the next 2 ranks are 2 and 3. So what we do is we divide, we look at 2 and 3, we see what's in the middle. You could actually use the mean if you want to. I've just chosen median because you can easily see it if you lay all your scores out on a line. The median of 2 and 3 is 2.5, right? So this is why you need to keep track of the ranks as you go. What I tend to do is across a page somewhere, piece of scrap paper, I'll have all my scores in order, and then I will write my ranks underneath and I will keep crossing them off as I go so I know that I haven't lost my place or done something silly. Now, if you don't do this properly, your calculations will be incorrect and you'll end up in a bit of a mess. A good rule to go by is ask yourself, do you have ranks that reflect the number of scores you have? Now, in this case, I have 20 scores in total because I have 10 participants per condition and 20 is my highest rank. So that's fine, that fits in. Now, if you have a lot of tied scores, then you may get a lower highest rank. It may be that your highest rank is 18 because you've had to divide your ranks up so much. But you should not have a higher rank than number of scores in your data set. If you do, something's gone wrong. You're going to have to go back and look at it again. Right, so we'll see here how this has worked. Now, we see across the scores here, just ignore these in red, these are the ranks. The numbers in black are the scores, and we can see that 10, across the whole data set, 10 is the lowest score. We give it the rank of 1. Let's look for our next score. We've got an 11 there. We've got an 11 there. We don't have any 11s there. Now, we've already looked at why 11 gets a rank of 2.5. There we are. Our next score should be 12. We don't have a 12, so there's a 13. So you see that 13, there is only one 13. That gets the rank of 4 because, of course, we've used up the rank of 2 and 3 with the 11s. Yeah? Just go with this. Just go with it. Work through it systematically. You'll get there. Now, let's look at our next score. Okay, there's a 15 there, and there's a 15 there. We have 2 15s. We don't have any more, so we give them the rank of 5.5 because, of course, our previous rank was 4. So 15, 15, we would go 4, 5, 6. So we take the median of 5 and 6 is 5.5. And so you go along with your ranking until here is our highest score, 27, and our highest rank is 20. It's worked out quite nicely. But as I say, if you have a lot of tied scores, you might find that your highest rank is a little bit lower. What you do is sum the ranks for each condition. Now remember I said ranks here. You don't sum condition A scores and you don't sum condition B scores. You add up the ranks of condition A and the ranks of condition B. Just ignore all these scores for now. Just ignore them. You're really looking at the ranks now. So add up all of these, add up all of these. So in our case, that data set, the sum of ranks for condition A is 72.5. The sum of ranks for condition B is 137.5. Remember, that's the ranks, not the scores. Now, if you have samples of an equal size, for example, your condition A may have 9 participants, condition B may have 10 participants. It's very easy for you in that case to find your U value. You just look at the smaller of the two summed ranks. Don't look at the smaller group because that might not have the smaller ranks. So if condition A with 9 participants has a higher rank than condition B, don't choose that one. Choose the smaller of the two summed ranks. Then you've done it, you've got your U value. And then you can kind of breathe a bit here. Now, if your samples are of equal size, as my example is here, then you have to go through some further calculations. It's very straightforward though, so don't worry about it. So to find your U score, you do this calculation. You take the number of participants in A, you multiply them by the number of participants in B, you then add this number to the number of participants in A multiplied by the number of participants in A plus 1. You divide that by 2. You remember to add that to that, and then you take away rank A. Whatever your rank A score was, you then take that number from that number. You should not end up with a minus number here. So if you end up with a minus number, something has gone wrong. Let's have a look at how this looks mathematically. So UA, number of participants in A, we had 10, multiplied by the number of participants in B, we had 10. We know that 10 times 10 equals 100. Okay, so far so good. Now we move to this sum. Number of participants in A is 10, multiplied by number of participants in A plus 1. Well, that's 10 plus 1, that's 11. So we multiply 10 by 11. That gives us 110. We then divide that by 2, which gives us 55. So we know that we have to add 100 to 55. And what does that equal? Well, nice and easy sum. It gives us 155. Then we take away rank A, and we know that rank A is 72.5. So we take 72.5 away from 155, and we have got 82.5. So that's our that's our UA value. So now we move to B. You do exactly the same for condition B. So condition B is going to be the same sum apart from the rank B bit, because obviously the groups are the same size. So this part is exactly the same. 155 minus rank B. Remember, rank B was higher. It was 137.5. So that gives us a UB value of 17.5. As I say, if you end up with a minus number here, go back, you've done something wrong. You select the smaller of these two values. Which one is lower? Well, you don't need a degree in maths to know that 17.5 is lower than 82.5. So UB becomes simply our U value. And you're now thinking, great, that's it, finished. No, it's not. There's still more. Now you have to go to your statistical tables, which you probably will not have used before, unless maybe you're doing maths with stats in. Now the first thing to decide, well, not to decide, I mean you already decided this when you wrote your introduction, is your hypothesis, whether it is one-tailed or two-tailed. Confusingly, for psychology students, there are two terms that mean the same thing. One-tailed is a directional hypothesis. Two-tailed is a non-directional hypothesis. A directional hypothesis is one which predicts the direction of difference between the two conditions. For example, Loftus and Palmer. A directional or one-tailed hypothesis would sound like this. Participants who are given the verb smashed in the critical question will estimate higher speeds in miles per hour than participants who are given the verb contacted in the critical question. You are putting it out there, you are going out on a limb and saying, I think this is going to be higher than that. Now, if you want to hedge your bets, you want to be a bit safer, you go two-tailed. You go for a non-directional hypothesis. So you always start your non-directional hypothesis. There will be a difference. We're not saying which direction the difference will be. There will be a difference in speed estimates in miles per hour, depending on whether participants are given the verb smashed or contacted. Yeah? So go back to your hypothesis and ask yourself, is it directional or non-directional? Yeah, and then you know whether it's one-tailed or two-tailed. Now we're going to look at how to find the critical value. I'm going to move on now to the table because it's easier for me to show you it and explain by looking at the table than just by telling you. Right, can you all please make sure that you are looking at the right table? Is your design independent measures? Have you used a directional one-tailed hypothesis? If you can answer yes to both of those questions, carry on. If you answer no to both of those or one of those questions, something's gone wrong, you need to go back and check again. I'm going to assume that we're all on the right page here. You're with me and let's keep going. Right. What we do here is look across this line here. You see this NB simply means the number of participants in one of your groups. And for the purposes of statistical tables, it's the largest group. So you look along this line and you stop. Oh, we had 9 participants in our largest group. But you might say, hang on a minute, both my groups were the same size. Okay, so both your groups were the same size. So you had 9 in each. So 9 is there and 9 is there. That's fine. You will just meet in the middle somewhere where they meet. So don't worry. This is designed to help those of you who have different size groups. Start with the largest size group, go along the top. Yeah? But if they're both the same size, they're both the same size. There's no hassle. Now we go for the number of participants in the smallest group. Again, if they're the same size, just go with it. It's not a problem at all. So you can see how this is going, yeah? You're going to be aligning one of these numbers with one of these numbers and seeing at which point they meet, right? So let's have a look. We have got a couple of scores we're going to look at here. So we have a critical value of 24 for a sample that had 10 in one condition and 9 in the other condition. So you see there's number 10 there, and we go down until we hit there because that meets the number 9 for the other group. Yeah, so group B has 10 participants, group A has 9 participants, or largest group has 10 participants, smallest group has 9 participants. So, and you can see if you do it the other way around, you get exactly the same sum anyway. If you go 9 there, 10 there, doesn't massively matter, to be honest, as long as you've got your sample numbers correct. As long as you know that, oh, in one group we had 10 participants, the other group we had 9. It doesn't matter whether you start there or you start there. You're going to get the same number. You can see how the numbers go. So this gives you your critical value. That is your golden number by which you measure everything. You measure the significance of your result, okay? So do write that down and make sure that you've got the right number. Use a ruler or something maybe to help you. Right, you do this if your hypothesis is non-directional, two-tailed. So it's a slightly different table. Again, you do exactly the same thing. You go along and you find the number of participants in your largest group, or if they're the same size, it doesn't matter. And again, you find your number of participants in your smallest group. You do exactly the same thing, but this is for a non-directional hypothesis. Don't use the wrong table because you will get the wrong result. And again, here we have a group of 10 and a group of 9, but you will notice that we have a different critical value here. The critical value this time is 21. This is just because it's a directional hypothesis. Yeah, it's just, it's a non-directional hypothesis. It's a two-tailed hypothesis. So it gives a different critical value because of the nature of the hypothesis. You don't really need to know anything more about that. But again, you can look at the critical values here and see that 9 and 10 meet there, and there is your critical value of 21. Yeah, so that's okay, isn't it? Right. Okay, so in our study, the data I've shown you, the critical value for a one-tailed test at the 0.05 probability level, where n1 equals 10 and n2 equals 10, that's just, per condition, is 27. Can you find this on the table? Should we go back? It was, so it was n1 is 10 and n2 is 10, and it was one-tailed. Let's have a look. We know that's two-tailed. Let's have a look at one-tailed 10 and 10. Yeah, there we are, 27. Yeah, 27. Okay, so it worked with this data set of two groups of 10. That's what we get. Yeah, okay. So you'll notice that it's a different number with the two-tail. So do make sure that you're using the correct table. So our U value, remember we had already calculated our U value at 17.5, so it's less than 27. Now if you have a U value that is equal to or less than your critical value, you can claim significance. So 17.5 is less than 27, so we can say we have a significant result. We can reject the null hypothesis. The IV has had an effect on the DV. Now, if your U value is more than the critical value, then you cannot claim you have a significant effect. You accept the null hypothesis. In other words, the IV has not had an effect on the DV. It's absolutely fine if that happens. It doesn't matter. You are students carrying out a piece of research, replicated research with a very small sample in less than perfect conditions. It doesn't matter. It doesn't mean that someone who got a significant result carried out a better study than you. They didn't. It's just that's the way it happened. It's who knows why it happened. It's just that's the way it happened. But this is just to show the person marking your IA that you understand the statistics and you can use them and you know what significance means. So you write up your result. Now if you write it up like this, you will be fine. If you try and change it and write it your own way, you might be fine, but you might end up in a bit of a mess. This is to guide you as to what you should be writing in your statement of significance. You get a mark for a statement of significance. If it's badly done or wrongly done or doesn't make sense, you're not going to get that mark. So I offer this as a suggestion. Obviously you fill in your blanks there, you make sure that don't write that you've got a significant result if you haven't. The number of times over the years I've marked an IA that tells me, it states that we didn't get a significant result because our statistics don't back it up, and then when they write the statement of significance they say we got a significant result, and I'm thinking you've just told me you didn't. What are you talking about? So you've got to be really clear and consistent on that point and accurate. This is where accuracy is important, accuracy in your maths. That is the end of the Mann Whitney U test. So if you did independent measures, you can go now. You're finished. Yeah, this next bit of the PowerPoint does not relate to you at all. The rest of you, you can come back into the room because we're now looking at the Wilcoxon T Test, which is for repeated measures. On the analysis section of your IA, when you've finished writing about descriptive statistics and you've got the subheading Inferential Statistics, you need to write this. You really just need to write this. I'm giving you that. There you are. It's a gift. Now, what you do is get your scores from your experiment, get your data. Now, of course, you don't have two groups because you have one group of participants. There they all are. There's 13 of them. And you have their scores for condition A and their scores for condition B. Write them out like this and leave some space here and leave a bit more space there because that's where you need to make your little mathematical notes and things. Now, what you do, first of all, you subtract the first score in A from its corresponding score in B. If you want to, you can do it the other way around. You can take B from A. It doesn't matter, but please everybody, notice the importance in my voice. It's important that you are consistent in your subtractions. In other words, keep subtracting A from B or B from A, whatever. It doesn't matter. It really doesn't matter whether you go B from A or A from B, but don't keep swapping them over. If you're subtracting A from B and then you start taking B from A, oh my goodness, it's going to be so bad. Now, you might find that when you start subtracting them, you go, hang on, you can't take 14 from 12, it doesn't work. It doesn't work, but that's why we're going to use a minus sign, yeah? That's the whole point. So don't make the numbers fit your calculations. Use the formula and just stick with it. Because students have done that in the past and it's been a real mess. Don't be one of them. So this is what we do, right? 12 from 14 is 2. 14 from 16 is 2. 15 from 12, oh my gosh, it doesn't go. Well, no, it doesn't, so we put minus 3, etc. So you will end up with a list here, a nice column of differences between A and B. As I say, it doesn't matter at all whether you take A from B or B from A because you're just going to be counting the nature of differences, right? So don't worry, there's no magical kind of, secret to this. You just take A from B or B from A. It doesn't matter because these numbers here are kind of unimportant. What's important is the sign, is whether they're positive or negative integers. We got that? Good. Pardon me, I'll just take a drink of water. Now you'll notice participant number 10, they have fulfilled, they've got all null hypothesis on you because they have got scored 8 in condition A and 8 in condition B. So the difference in their scores is 0. They're kind of upholding the null hypothesis here, aren't they? There will be no difference in the conditions. So we're going to come to that in a minute. Now, what you do is rank the differences, including the signs, to show the original negative or positive difference. Again, note any repeated scores. More than the same score more than once. Yeah, I'm starting to, I've been talking so long, I'm starting to confuse myself. You should use the medians to decide the rank. In this data set, there are 4 difference scores of 2, which is the second lowest score. 1 is the lowest score, is given the rank of 1. Now you'll see what I mean in a minute. You're thinking scores, differences, ranks, what you're talking about. You will see in a minute. As there are 4 scores of 2, when I say score, I mean the difference. We're looking at the scores of differences. They can't both be given the rank of 2, so you give them the median rank between 2 and 6, which is 4, because we've got 2, 3, 4, 5, 6. Yeah? So this is why you need to keep track of the ranks. Or maybe there are more than 4 scores of 2. 2, 3, 4, 5. So yeah, there must be more. There must be 5 scores of 2. Sorry about that. We'll just check that in a minute. Okay, so if you have any participants who scored the same for each condition, look, participant 10 scored 8 in condition A and 8 in condition B. giving them a difference of 0 and a rank of 0. You can't rank a 0, yeah, it just because it doesn't exist, if you know what I mean. So what happens here is you just have to take that participant out of your data set. They can't be part of the data set anymore, really, because they're supporting your null hypothesis. They have no data in a way, because they've shown that there is no difference in conditions. So you remove them from your data set, but you must remember to reduce the number of participants in your sample. So I had 13 participants in my original sample. I must now reduce my N number to 12. I have 12 participants in sample because participant number 10 is very awkward and has scored the same in both conditions. I have to zap them out of my set. So cross a line through their scores and remember to reduce your N number. Right, now you will know, annoying. Now you'll be able to see properly what I'm talking about. Okay, yeah, that's what I wanted to do. So all these numbers, they're addling my brain. So what we did here was we took A from B and we ranked the differences. And participant number 10 got 8 in both conditions, so we took them away. We said we don't want you anymore. And I think I have managed to obscure my scores at the bottom. Don't worry about it though. What I think we'll do here is we'll just take this away for a minute, just so you can see properly what I'm talking about. Oh, I'm really making a mess of this. Sorry about that. Let's just move that. Is that going to move there? I know what to do. Bear with me. My students are used to this. They're used to me kind of having to improvise sometimes. I'm just going to put, yeah, I don't think I'd put a little exit one on that. Let's try again. It's fun when things go wrong, isn't it? Woohoo! It's happened. Right, so we have all our scores here and all our scores here. We have our participants here. We know that we've taken condition A away from condition B, and it's given us this difference, and it's given us this difference and this difference, etc., etc. We know that with participant 10, they scored 8 in both conditions, and we're going to draw a line through them and forget them. So we now have 12 in our sample instead of 13. 13's unlucky anyway, we don't want 13. Now we have these differences here, and what we've done is we've ignored the 0 because it doesn't exist, and we have ranked, not these, don't look at the scores anymore, we're not interested in them, we're interested in the differences. Our lowest difference is 1. We give that the rank of 1, and look, we're keeping the signs. This one is a positive number, so it's +1. Yeah, so we keep the sign. Yeah, keep the sign there. So then we had 1, 2, 3, 4. Yeah, we had 5 differences of 2. I said 4 earlier. I actually meant 5. So in the median of the ranks of 2, 3, 4, 5, 6 is 4. So every difference of 2 gets a rank of 4. +4 there, +4 there, +4 there, and +4 there. They all happen to be positive numbers. Okay, so what's our next highest? It's a 3. So we've got 1, 2, 3 differences which have come up as 3. So we give each of these a rank of 8. Now you're thinking, why is it 8? Because our last rank that was accounted for was a 6. 2, 3, 4, 5, 6. So then our next 3 ranks are going to be 7, 8, 9. The median of 7, 8, 9 is 8. So we go -8 because that was -3, +8 because that's +3, -8 because that's -3, etc. And you will notice, very conveniently, that our highest difference is 8 and our highest rank is 12, and now we have a data set, a sample of 12, so that's worked out nicely. If you find that your highest rank comes out higher than the number of participants you have, something has gone wrong. It might come out lower because you might have so many tied ranks, so many differences that are the same, that it's actually evened out, to a lower highest rank. But if your highest rank is higher than the number of participants you have, that's not possible. Something's gone wrong. So you need to go back and have another look at it. Right, so in the case of a zero difference, you get rid of that participant. So we've talked about that. You reduce your data set. Now what you do, you've got such easy maths compared to the people doing the Mann Whitney, you should be really happy. Sum all the positive ranks. There we are. All of the positive ranks are summed and we get 62. Sum all the negative ranks. I think we only had 2, didn't we? I think that was right. So you get 8 plus 8, you get 16. You don't put the minus values in though when you sum the negative ranks. You know that they're minus numbers, and you just add them up accordingly, but don't keep in the minus number. Take the smaller of these two values. Again, you don't need a degree in maths to know that, yes, 16 is definitely smaller than 62. I just had to check, I just kind of little call to, the Dean of Oxford University to make sure that I understood that 16 is smaller than 62. You take the smaller of these two values. This is your t value, right? Don't you just love the way that maths uses lots of letters all the time just to confuse everyone? This is your t value. Therefore, your t value is 16. So for our data set, it's 16, right? So we don't want that big high number, we keep that number. Now what might happen, and what has happened in the past, is students have only positive rankings or only negative rankings. So they might have, all positive and 0 negative. And they always say, something's gone wrong because I've got 0 for one of my rankings. And I'm like, no, that's brilliant. Because if you've got 0, 0 is lower than any number in the world. So you take your t value as 0, and you've got a significant result because 0 is lower than everything. Yeah. So if you get 0, fine, you've got your significant result. Now, what you need to do now is go to your statistical tables. You may not have seen these before. They're fairly straightforward to use. Before you go there, you have to look back at your hypothesis in your introduction. And you have to ask yourself, is my hypothesis one-tailed or two-tailed? In other words, is it directional or non-directional? If your hypothesis is one-tailed, directional hypothesis, you have predicted the direction of difference in your experiment. So, for example, Loftus and Palmer, a one-tailed directional hypothesis, you might have written something like participants who are given the verb smashed in the critical question will estimate higher speeds in miles per hour than participants who are given the verb contacted. So if you've written something like that, then you've got a one-tailed / directional hypothesis. If you've written something like there will be a difference in estimated speeds in miles per hour, depending on whether participants are given the verb smashed or the verb contacted in the critical question, then you have a two-tailed / non-directional hypothesis, right? So you will have to look back at your introduction and you will have to know what type of hypothesis you've written. We're using the 5% probability level. That means that there is a 5% or less probability that your results were due to chance. So if you find a significant result, you can be pretty confident that it was the effect of the IV on the DV. Now, what we're going to do is look at a statistical table now, and for you to find your critical value. You have to find a critical value based on your t value, okay? So remember that you're going to be basing your the initial part of this use of the critical table on the number of participants in your sample. Remember, if you had any 0 scores, 0 differences, you must remove that participant so that you reduce your n value. Right, so if your hypothesis is non-directional, two-tailed, yeah, so there will be a difference, not predicting the direction of difference, you use this table here. You do not look at these columns, just ignore them. They have nothing to do with you. So we look down this column here, yeah, this is the one we want. Then we match that to the n value. So remember, the n value is the number of participants in your sample, adjusting for any that you need to remove. So in this example, let's say there are 18 participants, so you get your critical value is 40, right? So you have 18 participants and you've checked that you didn't have to get rid of any participants. No one had the same score, for example. So that's what you would look at. Now, if my hypothesis with my data set had been non-directional, with a sample of 12, remember it was 13, but I had to get rid of one of my participants because they inconveniently got the same score twice, then for a data set of 12, my critical value would be 14. Okay? Right. Okay, there we are. Now, if you have a one-directional hypothesis, then you use this column here. Don't go there and don't go there. Yeah, we just want this one. And again, find the n value in this column. So for 12, for my purposes, yeah, the value is, the critical value is 17. But let's say we had 18 participants and we've got a different critical value to the one for 18 participants with the non-directional hypothesis. You'll notice this is why it's important that you choose the right table, because they give different results depending on the hypothesis. Okay, so if your n value is 18, then your critical value is 47. If your n value is 12, your critical value is 17. Yeah, don't go there. It was very difficult for me to find some really good statistical tables online. This is the best I could do, I'm afraid. But remember to go beyond. Don't go there. That's your 0.05 column, okay? So, in our study, the critical value for a one-tailed test at the 0.0 probability level, blah, 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 with n equals 12 is 17. We've just found that on the table, haven't we? Our t value is 16, so that's less than 17. Now, the thing to remember about writing up psychology reports is not to say, it's only just significance, because 16 is really close to 17. Don't write that. You just write whether it's significant or not. It's like saying the difference between being alive and being dead is being a little bit alive. No, you can't be partly dead. You're either dead or alive. And that's the same with significance. It's either significant or it's not. It's not really significant or not very significant or like totally significant. It's just significant or it's not. Okay? And please, when you're rewriting your IA, when you're redrafting it, leave out all adjectives and adverbs and modifiers and intensifiers. So very, really, quite, a lot of, huge, small, this, that, you can say small sample. Okay, you can say a small sample. But if you say tiny sample, or, I would replicate it again with a huge sample. It's too over the top. Keep it pared down, because words matter, because you've only got a few of them per section. So if your t value is less than the critical value, then you can say that you have a significant result, and you can then reject the null hypothesis. Dun, dun, dun. So our t value is 16, that's less than 17. We have a significant result, people. We can reject our null hypothesis. Don't worry if you can't do this. Who would really expect you to be able to find a significant result? Your students. You've got small sample, you've got less than perfect conditions. It's highly unlikely that you would find a significant result anyway. Now, if your t value is more than the critical value, then you can't claim, here we go again. You can't claim significance, you have to accept the null hypothesis, etc. So you write up your result. Literally just take this. I'm giving it to you as a gift, and just insert whatever is relevant according to your IA, your study. You can try and write up your significance statement differently if you want to, but you might find that you come unstuck and it all gets a bit messy, right? I think that's it. Yes, oh my goodness, it was such a long video. Now, you might find that looking through this, you're thinking, oh my goodness, I don't know what to do. Well, just wait. Wait until we're in college and we can do it face to face. But if you really want to do it and get on with it now, then that's brilliant, you do that. If you're not one of my students, then please ask your teacher, or maybe just, work it out on yourself. But good luck, and I hope you get a significant result. Bye bye.